Welcome to our workshop. Successful software systems grow, and so do the automated test suites. Some of the customers we work with have thousands or tens of thousands of automated test cases, and it takes days, weeks, or sometimes months to execute them in full. But from a feedback perspective, that's very slow. If I am a developer and I make a change, it's painful to have to wait weeks or months to know if I broke anything. It's painful because there's so many things I did in the meantime that could have caused the bug. And it's also painful to have to wait another week or month to know if my fix broke anything else. And a straightforward solution to provide quick feedback, even though we have long-running test suites, is to select a subsuite of the test suite that we execute more frequently. It must be quick, but if we execute this quick subset frequently, then developers get quick feedback for that subset. Now the trick is to select this subset in such a way that it finds a large percentage of the bugs in a small amount of time. And in this workshop, we want to explain and demonstrate two different approaches for selecting this subset. And before I start, we are a small group, and this is good for having discussions. So if you have any questions, please don't wait until the end. If you have a question or if you have any other comment, just interrupt me either via the microphone or via the chat. We will do the workshop in 3 parts. In the first part, I will do the basic ideas and the research results we have for the different approaches. In the second part, Fabian will give a demo. And in the third part, a case study about how we introduce that at the customer with some tangible numbers. I said that we have many customers whose software test suites are growing. So if you have the same problem or same challenge in your organization, you are in good company. This is the logos of the companies that registered for today. And for the first time, we had scheduled this workshop. Thanks for your patience, and I'm sorry we had to reschedule because of COVID. If you don't know us, we are a spin-off from the Technical University of Munich. We are 55 employees now, 50 of which are computer scientists, 20 of which have a PhD in computer science. So we are very focused on software quality analysis. Most of us are in Germany, some of us are in the United States. So chances are very good that you have colleagues of us in your time zone. Now, enough background into the actual topic. Most of the customers that have long-running test suites don't have unit tests that are very quick that are causing the challenge. Instead, often the long-running tests are end-to-end tests or hardware-in-the-loop tests, or some other test that requires a third-party system, for example. And these tests tend to be hard to parallelize. So like the academic answer of, why don't you do a test pyramid? Why don't you simply do a lot of very quick isolated tests that can be executed in parallel? Really doesn't help them, because typically those historically grown test suites have a lot of end-to-end tests or other long-running tests that are hard to execute in parallel. And what really helps here is to select a subset of tests that we execute more frequently. And the first approach I want to explain is called test impact analysis. And the basic idea is that we look at what changed since the last time we executed tests, which parts of the systems were modified, and then select the test cases accordingly so that they execute those changes. And I first want to demonstrate that with an example from our own development, and then with some research results. The tool we developed is called Teamscale. It implements those analyses, and it is a bit more than 1 million lines of Java code and JavaScript code. And this is a so-called tree map of our source code. The basic idea is that every rectangle is a component, and the size of the rectangle corresponds to the size of the component in lines of code. Now I do a drill down. Now every very small rectangle is a method in the code. We have roughly 50,000 methods in our code base. And I want to use this tree map visualization to show how changes in test coverage relate and how this provides optimization potential for test impact analysis. The example I have is a ticket we implemented when Java received a new language feature. Because we analyze Java code and have static analyses for Java, Teamscale contains a compiler front end for Java, a scanner and a parser. So whenever Java or other programming languages we support receive new language features, we have to extend our scanners and parsers. In this case, Java receives closures. And the code we touched when we implemented this feature is orange and red. Red means new methods, and orange means adapted methods. So we see that there's a bunch of methods that we had to adapt when we wrote this feature. Now, if we execute test cases, then only test cases that run through the modified code can find a new bug. And the basic idea of test impact analysis is to select those test cases that run through those changes and execute them first, because they're much more likely to find new bugs than other test cases. And for that, we capture test case specific coverage. That means for every single automated test case, we capture which part of the system this test case executes. And to give you an impression of how much data we can capture here and how much information this provides us for optimization, I have prepared a time-lapse animation of our test suite. I will now run the animation that executes 30 tests per second. All the methods that are executed by one test are displayed in one frame in white, and then it darkens to green so that we can see what was executed. Let me start the animation. I think it looks a bit like a weather radar. And you see that some parts of the system are executed by many different test cases. Other parts are executed less frequently. And whenever anything got executed, it gets displayed in green here. Now, I don't want to run the entire, I think it's 7,000 or 8,000 test cases we have now, but sorry. The basic point I want to make is, if we run the entire animation, most of the code that was orange and red is still orange and red. And that means it was not executed by any of the tests in our automated test suite. And that shouldn't really surprise us, because when we wrote those tests years ago, nobody thought that Java might get closures and that we should now write a test case for that. However, all the test cases that don't execute any modified code, they can't find any new bugs. And the basic idea of test impact analysis is to use this optimization potential and focus on those tests that execute those changes. And test impact analysis works in two steps. The first step is that we select all the impacted tests. Impacted means that they execute changed code. Based on the test case specific code coverage we captured at the last execution of that test case. And depending on how central to the system the functionality is we change, this can strongly or not so strongly reduce the number of test cases. In our example, it would have reduced from several thousand to, I think, 5 test cases and provided a very strong speed up. However, other areas of the system are executed by many test cases. And in those situations, it might still take too long to execute all of them. So the second step tries to order the test cases in such a way that bugs are detected as quickly as possible. And how does that work? If we would execute all the tests now, then many of them would pass and some would fail. The failures are depicted here by a red circle with a white cross. Now, in an ideal analysis, we would like to order them in this way, that all the failures appear upfront. Then after the first test case, we would know if anything broke, and could stop the pipeline here and cancel all later quality assurance steps in the pipeline or in the process, and tell the developers that they need to fix that before they can continue. However, obviously we can't always produce this order, because if we knew which test case would fail, then we wouldn't need to execute them. And there's a whole research area that tried very many different heuristics on which information to use, on how to solve test cases to quickly have failures. And we implemented many of them and tried them out in research projects. And the one we found works best is one that always takes that test case next, that per second of test execution covers most modified yet untested lines of code. So we always take that, let me repeat that. We always take that test case as the next test, that per second of test execution covers most changed, not yet tested lines. And this produces often an order like this, where the first failure is quite quickly. Now, which speed up does this provide? And if we take a small amount of the time we require for the entire test suite, which percentage of bugs do we find? And we've done a lot of research projects to answer that, both in student research projects like bachelor's or master's thesis, and by our PhD students in the company. And basically, to do that, you need a lot of bugs. You need bugs that the tests can find to see if we only select the impacted tests, which percentage of them do we find, and how quickly does that work? And we applied two different approaches. The first one is we looked at many open source systems and analyzed their entire version history to see at which points had a developer committed a bug that broke at least one of the automated tests. And can we find, how quickly can we find that with test impact analysis? The advantage of that approach is that it's very realistic. It's real world bugs from real world systems. The disadvantage is typically developers don't commit the bugs. They find them when they locally execute the automated tests. So you have to analyze thousands of revisions to find a relatively small number of bugs. But it's very representative. The second approach is we produced our own bugs by something called mutation testing, where you have an automated program modification that breaks the code in known places, and then you execute the tests to see if you found those bugs. The advantage of that approach is that you can produce very many bugs and have very fine-grained analysis results. The disadvantage is it's not as representative and might produce bugs that don't occur like that in practice. But the outcome of our results were that both approaches had a very similar picture. So we are very confident that this holds for very many different types of systems. And if we spend 1% of the time that it takes to analyze to execute the entire test suite, we find 80% of the bugs that the entire test suite finds on average. So if, for example, our entire test suite takes 100 hours, if we allow test impact analysis 1 hour of test execution, then we find 80% of the bugs that the entire test suite finds. And this allows us to frequently execute this short test suite, for example, for every commit or for every hourly build, and then find the remaining 20% when we do a nightly test run or a weekly or monthly test run as we did before. And for test impact analysis, if we can afford 2% of the time, then we find on average 90% of the bugs that the entire test suite finds. I think this is a very dramatic speed up, and this is not only because the idea and the algorithm, the optimization algorithms behind test impact analysis are quite good, but also because retest all is a very inefficient strategy. It's simply inefficient to always execute all tests. And how does that work in practice? we have to do a preparation step where we execute all the test cases so that we know for every single test case which code does this test case execute. And then we can store the test case specific coverage information in Teamscale. Now, every time automated tests are run, the continuous integration platform can query Teamscale to know which tests to execute now. And for that, Teamscale queries the version control system to know which changes happened, and then performs those two steps and outputs an ordered list of impacted tests, which we can then execute to quickly find new bugs. The problem with the solution is that it's for big systems and very large test suites, it's a lot of effort to all the time collect that information and keep that system running. To give you some numbers, we have customers that produce more than 10 gigabytes of coverage information in a single test run. And especially if you have development on many different feature branches and maybe have customers that have old versions of the software that they still employ and you want to test it for them as well. It's really a lot of effort to deal with that amount of data and to monitor if the entire system still runs and to keep up with changes to the continuous integration pipeline. So our summary from a couple of years of working with that is that test impact analysis is a good approach for teams that have a lot of pain in long test suite execution. But for teams where the pain is not quite as high, a solution that's maybe not as good, but a lot less effort might be better. And in the second part, I want to demonstrate Pareto optimization of test suites, which is a simpler approach that selects a subset of tests and requires less effort. And the basic idea behind that is that we do that optimization once, independent of what changed. So if we have the end, and why can that be a good idea? If we have the entire test suite, every test represented as a rectangle, then typically, if I have bugs in my system, one single bug does not cause a single test case to fail. Instead, depending on how central the bugs are, often a single bug causes many test failures. And for example, in my showcase here, I have the orange bug that causes 2 test cases to fail, the blue bug that causes 4 test cases to fail, and the purple bug that causes 1 test case to fail. And the idea of Pareto optimization is to select the tests in such a way that we have a high likelihood of having some of the failing test cases, independent of where the bugs are and which tests they cause to fail. Because to know that there's something broken, we don't need all the failing test cases for a bug. It's already very useful to have the first test case that fails and indicates that there's a bug. And it's a simple idea, but for me, the first question is why there's any optimization potential at all. Because if you just select 1/10 of a test suite and don't know what changed, my gut feeling would have been then we only find 1/10 of the bugs. But if we find 10% of the bugs and 10% of the time, we didn't gain anything. So I want to spend some minutes to explain why there's optimization potential. And the short answer is because there's a lot of redundancy in historically grown test suites, and we can squeeze out that redundancy by cleverly selecting the test cases, even though we don't know what changed since the last run, as we know for test impact analysis. And to make that more tangible, I want to show different test cases with different types of redundancy for a paint application. This is Pixelitor. It's in Java open source paint application. And this is the tree map for Pixelitor. Again, every rectangle is a Java package, and the size of the rectangle corresponds to the size of the component and lines of code. And now I drill in. Now every rectangle is a file, in Java a class. And a further drill in step, now every tiny rectangle is a method in Pixelitor. And what we did is for every single test case, we computed the test case specific coverage and drew tree maps that show the test case specific coverage. So if I do this for a bunch of tests of Pix Editor, and we look at the tree maps, then we see that some of them look quite similar and some look very different. And the key point I want to make is that depending on how similar test cases are, the coverage is quite similar. And this influences how quickly we can find different types of bugs when we execute them in different sequences. Let me show an example for that. The paint program has different blurs or filters. And one of the test cases we have is the test Gaussian blur test case. Everything that the test Gaussian blur test case executes is displayed in green here. There's a second test case, that's called test motion blur. And because it's also a blur, it executes a lot of the similar functionality that the Gaussian blur test executes. And here, the code that has not been executed by the tests yet, in this case, only by the Gaussian blur, is displayed in green. And the code that was already executed by the Gaussian blur and is also executed by this test case is depicted in blue. And you see that most of the code that this test case executes is displayed in blue. And that means this code was already tested by the Gaussian blur test. And since the specific part is green, the likelihood is very high that that if there are bugs in the blue code, either none of the test cases finds that or both of them find it. So it's sufficient if we select one of them if we quickly want to find bugs. Now there's another test case called test lens blur. Same result, a lot of blue code, not so much green code. And the fourth blur test is the test smart blur. So what does that mean for how quickly we can produce coverage? I have a diagram here that on this horizontal axis has relative runtime. So when we start the test cases, we are at 0. And if we executed them completely, we are here at the right-hand side. And on the vertical axis, relative runtime. And if we execute the tests in the order they are in the test suite, then usually all the cluster tests, in this case, all the blur tests, are executed one after the other. But that means that coverage rises quite slowly. The first blur test provides a lot of coverage, but the following blur tests add very little additional coverage. What we can do now is employ a similar heuristic like in the second test impact analysis step. That means we also always select that test case next, that per second of test execution covers the most so far untested lines of code. And if we do that, our algorithm proposes a different test execution order. In this case, the first one it suggests is called test create and modify selection. And again, because it's the first test, everything is green. The second one it suggests to execute after the test create modify selection is test change view settings. And the first thing that is immediately apparent is that test change view settings sounds like it tests something completely different than the one we had before, test create and modify selection. And we also see that, okay, there's some blue code, but the relative amount of green code is much higher. So it provides much more new coverage than the different blurs we had before. The third one is test second layer. The fourth one is test save image. And there's still a lot of green code here. So coming back to that diagram, this new sequence of tests produces a lot of coverage much more quickly. And that means if we cut the test suite here and only execute the first 5%, 10% of the tests, then in this order, we get a much higher coverage and hopefully a much higher amount of bugs we can find than if we just execute the first part of the test suite. And this is how Pareto optimization works. We compute test case specific coverage and we allocate a time budget and then compute which subset of tests that fits into this time budget produces the most coverage for that system. And how does this compare to test impact analysis? We feed less information into the system. We don't know what changed. So we expect not as good results, but we performed the same experiments on open source data and on mutation testing data. And we found that instead of 1%, it takes 6% of the time to find 80% of the bugs. And it takes 11% of the time the entire test suite requires to find 90% of the bugs. And in our estimation, this is still a very significant speed up. If I get 90% of the bugs in 10% of the time, then I can still get a much quicker feedback cycle for most of the bugs that occur during development. And the key advantage of that is that it's easier to handle and integrate and keep running in a continuous integration infrastructure. While test impact analysis requires continuous recording of test case specific coverage and a deep integration into the continuous integration pipeline, because every single time we run the test suite, we need to query Teamscale which tests to execute now. Pareto optimization is simpler. We still have the coverage recording step, but we only need to do it once. And then we run the analysis once and get an ordered subset of tests. And this test subset, because it's independent of the changes, is fixed. And we can integrate it into the CI pipeline once, and then we're done. I was a bit oversimplifying. Maybe we want to repeat this step every 3 months to have up-to-date coverage information. But from our experience, it's still way less work to set this up and to keep this running, and requires less hardware, and it's just easier to maintain. So let me wrap that up. Both approaches are valid on a cost-benefit spectrum. Test impact analysis has the better results, but is more costly. And Pareto optimization has not as good results, but is much cheaper to apply. For test impact analysis, we found 90% of the mutants. That means 90% of the bugs we injected or the bugs we found in the open source system in 2% of the time it takes to execute the entire test suite. For Pareto optimization, we required 11% of the time to find 90% of the mutants. However, test impact analysis is higher effort than Pareto optimization, where we have less maintenance and also probably a higher applicability, because it's easier to measure test case specific coverage once than on a continuous basis in the live test environment. This concludes the first part. Before Fabian starts with the demo, are there any questions, comments you have on test impact analysis and Pareto optimization as ideas or to our research results? Hi, Christian. I saw you joined since the beginning.
Hi, Elmar. Didn't found that one.
Fabi, it looks like you can continue with the demo. Yeah. If you think of any questions, just interrupt us and put them into the chat.
Exactly. Also feel free to interrupt me during the demo if you want to see anything in addition to what I'm showing, or if anything is unclear. My name is Fabian. I lead a team called Pilots at CQSE, which is the team that helps new customers get started with our analyses. So if you should decide to try out one of these analyses yourself, then you'll probably be talking to me again. And I'm going to show you a little bit how the test impact analysis works and how Pareto testing works. But before I dive into the actual demo and show you the tool, I first want to give you a little bit of context of what you're about to see, so it's easier to understand. What we're going to be looking at in the demo is we're going to do test impact analysis for Teamscale itself. So the software that we're developing in the demo is Teamscale, and we'll add a new feature to Teamscale and then see how test impact analysis handles the tests for that. Now, how do we develop and test Teamscale? We have a lot of different tests in the typical pyramid shape. So at the bottom, we have the usual unit tests that are very fast, only take 180 seconds in total to execute, but we have a lot of them. And then it goes up over integration tests, system tests, and UI tests. And the UI tests are, of course, the slowest. And we have not that many of those in comparison to, for example, the unit tests. So in our system, as is, we usually also see it with our customers, the most potential for optimization is in the highest level of test, so in the UI test in this case. So what I'll show is how we optimize the UI tests for Teamscale with test impact analysis. And we'll pretend that we are a developer of Teamscale and we implemented a particular feature. That feature relates to this page in Teamscale, where as an admin, you can enter credentials for other systems, like, for example, GitHub or some other Git repository, some SVN repository, or a Jira. So Teamscale can connect to these systems and talk to them and get information out of them. And so people enter usernames and access tokens here. And we built this to let people enter these credentials in a structured way. One feature that we forgot in the beginning and that we retrofitted later was to add a delete button, so you can actually get rid of these things again. And this is the feature that we'll use in the demo to show you how test impact analysis works. So just imagine you just implemented this delete button. All right, then I will jump over here. I'll just move my slides out of the way. Now, what you see here is my browser and the login screen to Teamscale. So Teamscale is a server application. It runs on a central server in your company, and everyone can access it via the web interface. I'll log in here with some super secret credentials for this demo instance. And I'll quickly explain a bit how the UI works in Teamscale so you know what you're seeing. On the left-hand side here, we have a lot of so-called perspectives. Each perspective shows a different view on the data that we have in Teamscale. And this can include things like the test impact analysis and Pareto testing, which you could find here, for example, under test gaps or under metrics, tests, and so on. But it also includes views on other things that Teamscale can do, like static code analysis. We have the findings, or architecture analysis, and so on. We are currently on the activity perspective, which gives you the sort of history of your code that you're used to from your version control systems. Like, for example, Git gives you this kind of commit graph, or SVN log would give you the same thing. On all of these perspectives, you can at the top select which project you're interested in, because you can have multiple projects in Teamscale. So if you have like 10 repos, you can have 10 projects. And you can also select the branch that you're interested in, because by default, Teamscale talks to your version control system. And if you create a new branch, it will automatically show up here, so that we can also run all of the analyses on all of the branches that you have. And what we can see here is that Teamscale already knows about the latest change that we made, which was to implement this external credential deletion here. So we are Florian in this demo, and we just implemented this feature. We committed this and pushed it to the version control system. And what is the first thing that happens when we do this? Of course, our automated CI pipeline starts running. And this is what I'm gonna simulate now. So I'll start the CI pipeline. This is now going to start building Teamscale. And then once it's built, it's gonna start running the tests. And in the CI pipeline, we already integrated test impact analysis. So this is not gonna try and execute all of the tests, which would take like 45 minutes, and then that would probably be a very boring demo, but rather it's just going to execute the tests that Teamscale thinks are impacted based on the changes that we did. And I can quickly show you which ones those are, because this change here is also linked to an issue from our Jira, and I can just have a look at that issue, and in that page we can also see which tests are impacted. So here you see that this is the meta information from Jira, so who's the assignee, what's the priority, what's the description of the issue. Teamscale also knows all the files that we changed when we implemented that issue, and then based on those changes, it calculates the impacted tests. So instead of running all of the several thousand tests that we have, and in particular all of the over 200 UI tests, it only selected 4 different tests to run in this case that are actually running through these changes that we made here. Let's quickly see how far the pipeline is. It's starting the tests now. So we should hopefully only see 4 tests being run. And these are UI tests, so a browser is going to pop up, and you'll see a different instance of Teamscale where the tests are being performed on this external credentials view. While this is running, one side note, these are of course automated tests. It's also possible to do the same thing for manual tests. So if you have a lot of manual tests where it would be a good idea to save time by not rerunning tests that don't actually run through the code changes, the same thing can be achieved as well. The basic technology is also the same. We do the same kind of coverage recording just while you're running your manual tests. And we just need a bit of integration with whatever tooling you're using to manage the manual tests. As you can see here, these are the automated UI tests that are running now. So the robot is clicking through the UI and trying out this external credential view and some different tests on it to see if it still works. Should be done any second. All right, and it's done. So what happened here? We actually executed 5 tests now, not 4. So these are the 4 that Teamscale had selected based on what it knew about the system. There was actually a 5th test that was new. So Teamscale didn't know about it yet because we implemented it in the commit that we just made. But Teamscale, of course, realizes that there are more tests now to execute than there were before because we have added this one. So it also selected this one in this case. And this is actually one that failed. So this whole thing took 2 minutes, 59 seconds, so about 3 minutes, which is a pretty good speed up compared to 30 to 45 minutes that it usually takes to run all the UI tests. What also happened in the background is that this test-wise coverage was being recorded again for the test that we executed, and this has also been uploaded to Teamscale. We can see this again in the activity view if we switch back here, where a new entry has been created, which updated the test-wise coverage that we have. I'll quickly show what that actually looks like. If I click on any of those tests here, sorry, that was a bit too far. If I click on any of these tests here, then you get a tree map that shows you exactly which code the test runs through, and it also shows you, in this case, for example, that this test failed the last time I executed it. As a developer, I now got really fast feedback, and I know something is wrong with the change that I made. So what is the next step that I do? Of course, I fix the bug. So I debug what is going wrong here and why this can delete external credentials test is failing. And then it pushed the fix to a version control system. I'll also simulate this. So I have a little script that can automatically fix the bug that we have in here, and then runs the same CI pipeline again. And we can now switch back to activity here, and we can also see that Teamscale picks up the change that we committed. It's analyzing it as we speak. So it realized that something new is in the version control system, and automatically runs the analysis again. And as you can see, this only takes a few seconds because we only changed one file, and Teamscale does incremental analysis. This means that we only have to analyze whatever you check in as changes. We don't, with every check-in, we don't have to reanalyze the whole system. That makes the feedback loop very fast here. Now, if we go on that one change that we performed here, that is the bug fix, we can also show impacted tests just for that one commit that we made. And for this one commit, Teamscale calculated only one impacted test, which is exactly the one that was failing before, which is also one strategy that is very important to apply. Whenever we have run a test and it has failed, Teamscale will always tell you to rerun that test to make sure that to check if maybe now it doesn't fail anymore, even if there were no related code changes. All right, let's see how far we are. It's going to be running that test pretty soon. Here it comes. So we'll run through that test again, see if now our fix actually worked, and we can now actually delete the credential as we wanted to. And that looks pretty good. The test passed. So this whole thing took like 1 minute, maybe 2 minutes to rerun this again. I'd also like to show you what Pareto analysis looks like in here. We can find that under test gaps Pareto ranking. If I click here, I can make a little selection. Which tests do I want to perform the ranking on? Maybe I want to do it for all the tests that I have, but maybe I only want to do it for very long running tests or only tests that are in a certain package and so on. This is a very flexible way to select the tests that I want. For the demo now, I'll just do it on all tests. So I click compute ranking, and then Teamscale computes the optimized test list and also shows you this curve that we had before. So for your system, you can immediately see what would the potential speed up be. And I can also move the slider here to interactively select a certain test budget. So for example, I only want to spend 2 minutes testing, and then it will immediately tell me which tests would be selected for those 2 minutes and how much coverage would I achieve. And then I can move the slider until I'm happy with whatever I see. Any questions about the demo so far? Otherwise, I'll switch back to my slides. So to sum it up, with regular CI, this whole demo would have.
So sorry, I just have one question.
Sure.
If you add a new feature, probably you are adding new test cases, unit tests, or UI tests, and probably those one are the first you need to execute. And I just have the question: do the developer execute them by themselves up front, or is it happening after the CI/CD delivery?
Yeah, very good question. So this is actually what also happened in the demo here. We added a new test case in the first commit that we made and that we tested. And because Teamscale realizes that the test runner that actually runs your test knows one test extra that wasn't there before, it will tell the test runner to always run that. So if you add new test cases, no matter what happens, Teamscale will always tell the CI to run those new test cases, because we don't know anything about those yet. So we don't know if they can find bugs or not. So it always makes sense to run the new test cases. Does it answer the question?
Yes, of course. But that means that you cannot implement a further bug if you don't have any strange cross effects in your system. Am I right?
I'm not 100% sure.
So if I change the behavior of my software and I cover this change by tests, which I do add, I can guarantee that those things are working and does not have any bugs. And probably as a developer, I have already processed those tests, and therefore, most likely, I don't expect that I get another issue if I have not a fragile system where I'm working on.
So we can't guarantee that there are no more bugs in there. So there might be bugs that your test suite just isn't able to find. That's the whole crux with testing. We can never show that there are no bugs in a system. We can only show that there are bugs in the system with tests. So there might still be additional bugs that your tests haven't found. But if you run the tests that Teamscale selects with test impact analysis, and you run all of the impacted tests, then we can guarantee that we find all of the bugs that the whole test suite would find. There are some corner cases where we can't guarantee this, which is, for example, if you have non-executable files that impact what the tests do, for example, like configuration files, and you change the configuration file, and Teamscale doesn't have coverage for that, so it doesn't know which tests are impacted by that, so it might not run all of the relevant tests. But if you only make a normal code change, then we have a very high security that we select the right tests.
I have one extension to the answer from a research perspective, because there's a research area called selective regression testing. And one subset of that area proposes so-called safe selection techniques. And safe means that they guarantee you that their selected subsuite will find all the bugs that the entire suite finds. In theory. In practice, it has two problems. First, it very often selects the entire test suite. Now that fulfills the guarantee, but it's useless in practice. And the second problem is that a lot of the assumptions behind safe regression test selection techniques don't apply in practice. For example, one core assumption is that if I have one system version and I execute a single test case 100 times, each of the 100 times it will exactly cover the same code. And this is often for complex systems not given because of caches, because of non-determinism in many code bases and so on. So our conviction is that instead of focusing on safe regression test selection techniques that sound better in theory but don't work in practice, we have an unsafe approach. Some bugs might slip through, and the very pragmatic solution to that is that every now and then you still do the entire run. So we don't do test impact analysis instead of running the entire test suite, but in addition to it. So that very often you have the quick feedback, and every now and then you still do the long run and find the remaining bugs that slip through the cracks. I hope I didn't give a too long answer, but that did that answer your question?
Yeah, that's great. Just get a little bit deeper into that. Yeah, thank you.
Thanks a lot for the question.
More questions? All right, then I'll sum up the demo. So with regular CI, the whole demo would have taken more than 30 minutes because running the first batch of tests alone would have taken so long. With test impact analysis, we were able to select a small subset of tests that also that were able to run in less than 5 minutes, and that surfaced a bug that we also fixed in that time, and then with less than 15 minutes, we were done with the whole feature. So that was a good speed up there. And this is what we want to achieve with test impact analysis. Now, in the next part, I'd like to give you a feeling of how you can find out for your own system if test impact analysis and Pareto testing are valuable there and work there, as we described. And of course, when you want to try something out like that, you don't want to spend too much time and effort just to maybe in the end find out it's not a good fit for you. So what we try to do is a so-called pilot project, where we try to show you with as little effort as possible what the value is that you can get out of the analyses. And I'll show you how that works on the example of Bayerische Versorgungskammer, or BVK. They are a large insurance company here in Munich, where we piloted both of the analyses to see which of those is the better trade-off for them. And I'll show you what the results were for those. Now, how does this normally work? We split the pilot into two phases, the blue phase and the green phase here in the slides. In the blue phase, we will do all the technical setup. So we will record test-wise coverage once and do a little validation to see that the data is actually correct and we don't have any technical problems. When we have that, we do the green phase, which is where we get the actual insights. Here we'll do a retrospective evaluation of what would test impact analysis and Pareto testing what would the results have been for you in a historic period of time. Usually we choose something like the past year or the past 2 years. Why a historic period? Because this way we don't have to do all the integration in your CI/CD pipeline, make it available to every developer and possibly disrupt their workflows and give them something new that they have to think about. But instead we can see with historic data what would the benefit have been for you if you had access to these analyses in the last 2 years, and then extrapolate from that what would the value be if you actually decide to go with these analyses and use them. As a little reminder, with Pareto testing, all we need is this test-wise coverage, and then we can collect a set of tests that are selected and prioritized. to show you what would the analysis do for you. With test impact analysis, we also need the code changes in addition. So this means we can't just look at the test, but we also have to look at the history of changes that you made in the last 1 or 2 years. How does this recording of test-wise coverage work in a little more detail? What you usually have is you have a test environment where you deploy your application, and then either some automated process is running that runs tests against that application, or some manual tests are happening where people are clicking through the UI, for example. What we do now is we install a so-called test-wise coverage profiler on your test environment, which is an additional tool that hooks into your application to find out, while these tests are running, which lines of code are being executed down here. And so this gets information like in this Java file, line 5 was executed, or in this C# file, line 15 was executed, and so on. And then this can write as a so-called trace file, which basically just contains all the lines that were executed during the test. Now, this alone is not test-wise coverage profiling. This is normal profiling that you maybe already know from your CI pipeline, where you maybe have it for your unit tests. What we still need in addition is to know when do test cases start and end, because then we can cut up this big trace file into smaller chunks, one for each test case. So we need some integration into your testing process or into your test tooling, so that we can send events to this profiler whenever a test starts and whenever it ends. And then this will automatically output us not one big file for all of the test suite, but rather one file per test case, where we know test 7 runs through these lines of Java code, for example. When we have this, then we can send that data to Teamscale. And once we have this test-wise coverage data in Teamscale, then we can play what if. So we can ask Teamscale what would have happened in the last 1 or 2 years when you were running tests in your CI pipeline. What would the speed up have been? Now, we did this for BBK for an application that they have, which is a Java business information system, which handles some sort of insurance contracts. And the first result you get out of this is, of course, the test-wise coverage that I've already shown in the demo. So you now know which test runs through which methods in the system. What you get in addition for free is, if we measure not just one test suite, but maybe different types of tests on different levels, you also, of course, get the coverage for all of these tests. This is usually also an interesting insight, because many of our customers have higher level tests like end-to-end tests or UI tests, where they don't even know what coverage those are producing. And with this coverage recording, we for the first time can actually show them which code those tests run through. So in this case, at BBK, we measured the unit tests, because those were very easy to measure. And then these are the tests that are actually long running, where we tried out test impact analysis and Pareto testing. GEFO test means Geschäftsvorfall tests. So these are tests that run through certain business cases and see if those work. And chain tests are tests where they chain up a lot of different tests in one go, so they don't have to redo all of the test setup for every single test, and speed them up that way a little bit. But this technical data that we get at the end of the blue phase that I showed before you is not really the interesting part. The interesting question is, what's the actual benefit for you that you would have had? So how much test time can we expect to save with test impact analysis and Pareto testing? And for test impact analysis, how we answer this question is as follows. For each day of development time in those 2 years that we looked at, we can find out from your version control system which changes did you perform on that day. So which commits did the developers do on that day. And for those changes, obviously your CI pipeline would have run. And so what we can do is we can calculate the impacted tests for those changes, and then see how long would it have taken to run these impacted tests on that day. And then we can do this for a lot of days, for the whole 2 years, automated. And then at the end, we get a total run. We can compare this to the total runtime of tests that you normally have in your CI. So if normally it takes 12 hours, as is for BBK the case, to run all the tests, then we can see how long would the impacted test cases have run in comparison. And then we can see how much speed up can you expect over time. course, there's going to be some days where it takes longer because you maybe modified some very central classes, and some days where it's shorter, where maybe you only had a few code changes and not a lot of impacted test cases. What did this look like at BBK? This was the histogram that we got. You can see it runs from July 2018 up until sometime in 2020. So we looked at roughly 2 years here. And on the left here in red, you can see the total runtime in comparison. So these are the 12 hours that they normally spend running their tests. Now, one thing that I really liked when I first saw this graph is when you draw a line here at half of the total test runtime, you can see that on almost all days, we're already below that threshold. That gave me a really good gut feeling. But to put the finger a bit more on how useful this would have been at BBK, we used a different visualization, a so-called histogram, where we sort all of these days into buckets depending on how long the tests would have run on that day. So all of the days that took less than 20 minutes of test time are in this bucket, and all of the days where it took, I don't know, over 8 hours are in this bucket. And as you can see, most of the days are in very low power numbers compared to the 12 hours that they usually have. So this also shows that there's a lot of potential for speed up here, where we can do the testing for a whole day in just 1 or 2 hours. To put it in numbers, on 93% of all days, the test runtime would have been less than 17% of the whole test suite. That was already very convincing for BBK. They like those numbers. And we, of course, also looked at what would Pareto testing do for them to see which of those 2 analyses would be the better trade-off for them. This is the result from Pareto testing. So again, the curve that you've seen on the slides before, but this time for the business information system from BBK. And as you can see, they have a very, very steep curve. So with even just less than 10% of test time, they are already here in the high 90s%. Actually, if we draw a line here at just 1 hour of test time compared to the 12 that they usually have, they already have 99.2% method coverage that the whole test suite would achieve. So that's almost everything. And that actually was a surprisingly good result for Pareto testing here, where in the end we said it probably makes more sense for them to implement Pareto testing because the numbers are so good here. Of course, one thing that might still go wrong with Pareto testing is, since we only select a static set of tests, we might accidentally select tests that don't very often run through the code changes that we make. So maybe we select a lot of tests for old code, but we're only working in new areas of the system, and then we would constantly be testing things that are not getting changed. So what we also looked at is to correlate this Pareto list that we calculate here with, so this 1 hour of test runtime, with the information we have from the test impact analysis, and see how often are the impacted tests that test impact analysis selects also part of this Pareto list, because that's something that we would want, that we regularly run through the actual code changes that people are making. And over those 2 years, on every single day, at least one of the impacted test cases was also in the Pareto list. So we're never selecting any tests, we're never selecting a list of tests that doesn't run through the code changes that we make. And on average, it's 70% or 17% of the test impacted test cases that are in the Pareto list. Those are also pretty encouraging numbers that mean that there's little potential of us completely testing something different than what people are working on in development. How could BBK be using these analyses? Because just knowing that they are helpful is not enough. We also need to know how should we apply them. And these are 2 suggestions that we made, how these analyses could have been used with them. What are they doing right now? Right now, they're doing rerun all. So this means that in the night, they run these 12 hours of tests, and then sometime in the early morning on the next day, people get feedback if they introduced a new bug. If we want to speed this up with test impact analysis, one thing that people commonly do is so-called time boxing. So during the day, we spend a time box of 2 hours to build the software system and then run some tests. And we use the tests from the test impact analysis in that time box. And then, of course, sometimes we would have time boxes where only very little tests are impacted because the code changes that were made in the last 2 hours didn't impact a lot of tests. And then maybe we're finished a little earlier. Sometimes maybe we modified something very central and then more than 1 hour of test time is selected and we would just cut off then and not run the remaining tests. It still gives us a good chance of getting feedback within those 2 hours on the changes that we did before those 2 hours. When we think back to the histogram that I showed you, most of the days were anyways in that 2 hour bucket or below. So there's actually should be very little slots where we run out of time with test impact analysis for BVK. So this should work very well for them. Of course, as Elmar already said, we'll still rerun all of the tests in regular intervals. Since they are running in 12 hours, it's still possible for BVK to do that, for example, nightly. Just to make sure that if, for example, we have a very central change here and don't have enough time to run all of the impacted tests, we can still catch the remaining bugs here. So again, this means BVK is not losing anything here. They still get the feedback the latest at night, but they have a really good chance of getting feedback much earlier and thus speeding up their development. For Pareto testing, our suggestion was very similar. We can also do time boxing there. In this case, we don't change which tests are run in each time box, but rather each time we just run the list that Pareto testing calculated for us, which takes 1 hour to run. We still rerun all of the tests nightly in case any bugs slip through this fast feedback, and we still get them in the same time frame that we had before. And then in longer time frames, for example, monthly or maybe every 3 months, they can update the Pareto list by re-recording this test-wise coverage and then getting a new list and putting it into the build system. Now, because the numbers were so good at BVK for Pareto testing, they decided to go with the option that is less effort to implement. It still gives them a good return on invest. So they actually implemented Pareto testing, and they are now regularly using it for multiple projects. We actually just onboarded a new project to the analysis last month. Since they've been using it for a while now, we did one final check to make sure it's actually working as intended. We looked at the number of failing commits and tried to find out how much test time are they investing and how many of those failing commits is Pareto testing actually finding. And it actually worked very well for them. So with just 5% of the test time, we find 70% of the failing commits in these regular daily 2 hour slots. So this means that on 70% of the commits, people are now getting feedback within 2 hours instead of within 24 hours that they had before. So they are very happy with that. Any questions on how these pilots work or how specifics on how we work with BVK on this project? All right, then one final word from my side. If you are interested in the analysis, but maybe you have someone else in your company that didn't have the time to attend the talk that you also have to convince, we're happy to come and hold the same talk that we just held now for you in your company. So if you want, you can contact us. This is for free. We'll just have a virtual meeting, and then we can also tell your colleagues how these analyses work. And in this context, of course, we can tailor it a bit more to your actual setting and probably go into more depth than we can in this workshop where other people are also attending. So if you have very specific questions about your setup, then we can probably answer them there. All right.
And let me wrap up. Thanks a lot for your time and for the questions you asked. We really appreciate that despite being at the peak of summer, you spent the time with us. We would be really interested in your feedback. And Lavinia will trigger a very quick feedback poll right now with 2 questions. And if you want to be notified about such talks, please subscribe to our newsletter because then you get an invitation in time. Thanks a lot for your time. Fabian and I will still stick around in the breakout rooms in case you have anything you would like to discuss in a small group. Otherwise, have a great evening, and I hope you find some way to refresh yourselves to cope with the heat. Thanks.
Have a nice evening.